All right, so we've been talking a lot about momentum and impulse, and today we're going to do an example that's a little trickier. It's not bad, but it puts kind of everything together in a way. Uh, and I looked at these stats from a Civil War reenactment troop. I don't, so I'm trusting them. I think they're pretty accurate. I did verify, but it says the Napoleon cannon used in the Civil War had a mass of 559 kilograms. So that's the mass of the cannon itself, which is just over 1,200 pounds, and launched a 5.5 kilogram or 12-pound cannonball a distance of 5 football fields. So if you picture this, you have a really massive cannon launching basically an object that's the mass of a bowling ball. It can launch it 5 football fields, which is a very, very good distance, a very far distance, I should say. And the question is, what's the momentum of the system initially? So this is a good question because, well, actually, before I go through it, let's read through the questions, and then we'll give you a chance to answer. It says, what's the momentum of the system initially? Okay. Letter B, what is the momentum of a cannonball fired at 439 meters per second? So this cannonball is going to be fired at close to 1,000 miles per hour. C, what's the momentum of the cannon? And then how fast will the cannon move backward? So go ahead, try this one out, and then when you feel like you've given it a good attempt, go ahead and come back and we'll talk it through. Okay, so a couple things. Letter A, what's the momentum of the system initially? Well, you have to figure out what I mean in this question by system. So if you look, the system consists of the cannon, and then inside the cannon is a ball. And so initially, before anything's fired, the momentum of the system is zero initially. And you might remember back to the conservation of momentum, which is whatever the initial momentum is before a collision, or in this case, an explosion collision, right? The momentum before equals the momentum after. So it's maybe starting to bug a few people because they're like, well, the momentum of the system before is zero, but after we fire the cannonball, the momentum of the cannonball isn't zero. Well, it's important to think about the whole system here. So let's take a careful look at this one. Letter A, the momentum of the system initial, we'd say P of the system, momentum of the system is zero. Okay, what is the momentum of the cannonball fired at 439 meters per second? So I mathed this out for us. So for B, we know that we have the mass of the cannon, so M sub C is 559, and then we have the ball, which the mass of the ball is 5.5 kilograms. We know the velocity of the ball is 439. So our momentum equation is actually kind of nice because we know that P equals mv. So for here, we just take 5.5 times 439, and the momentum of the ball is 2,414.5. And I didn't put the units there because I wanted to check. Do you remember what the units are for momentum? And we look at kilograms for mass. It's meters per second. So for momentum, it's going to be kilogram. Ooh, I should have not picked red. It's going to be kilogram meters per second. All right, and then we didn't focus so much on this so far in our videos, but it's important to remember that momentum is a vector. And I apologize for the little scribbles there, but when you crunch this, we got that was 2,414.5 kilogram meters per second, and I put that vector symbol up there, which means I'm also going to include the direction. And I'm going to say when that cannonball gets launched from this cannon, it's going this way, and I'm going to say that that's the positive direction. I just picked it to the positive to the right because it made sense to me. In my math class, down the x-axis to the right is positive, so that's positive to the right. Okay, so it says, what's the momentum of the cannon? Well, if you've ever seen in like a Civil War film or any kind of movie where a gun is being fired or cannon, the ball is going to go forward and automatically the cannon or the gun has to kick back. It's not a mystery, well, maybe it is kind of a mystery, but by the laws of physics, there has to be a recoil or a kickback because the initial momentum of the system was zero. So the momentum after the object is fired also has to be zero. So what I kind of did here in slappy handwriting, but I said momentum before of our system is momentum of the ball plus momentum of the cannon. And that's zero because nothing's moving. Well, just because we fire the ball doesn't mean that all of a sudden we have momentum that was created out of thin air. So what's going to happen here is momentum after for the ball, even though it's out here and it's moving forward very, very fast, that has positive momentum going this way. Well, since this part of the system has positive momentum, this cannon has to move backwards. And it has to move backwards with the exact same momentum that the ball has. And the reason why is because we got that this was positive 2,414.5. So the momentum of the ball is positive. Well, that means the momentum of the cannon, or the recoil momentum, is going to be negative. so that when you add those two momenta together, it still equals 0. So when you know that the momentum of the cannon is going to be negative 2,414.5, then we can actually figure out how fast the cannon recoils backwards. So notice here I put the negative in, 2,414.5 kilogram meters per second, divided by this time the mass of the cannon, and that's going to tell us that the recoil velocity is negative 4.32 meters per second. So that's that cannon that weighs 559 kilograms, it weighs over 1,000 pounds, is actually going to move backwards at 4.32 meters per second, or about 10 miles per hour. So when people are firing these weapons, you'd have to be really careful, because if you stub your toe in your house at 10 miles per hour, it hurts your toe. Now, could you imagine if this recoil, this cannon kicked back on you and it weighs 1,230 pounds and it's going to hit you at 10 miles per hour? So you'd have to be careful. But so if this cannonball goes forward, the cannon itself has to move backwards. And that's the conservation of momentum, kind of shown to you by some mathematics. So there's a video here. I don't know if I'll show the whole thing, but these guys are reenacting it.
We're going to sight this cannon in today. We got to adjust the sights and see if we can hit those targets down there. I like that before. Fire! Top by 4 feet.
Pretty intense group here.
Way high.
See the kick back there. And they're going to show you where that ball ended up.
This is the backstop, and this is theoretically what stops all the projectiles from
And I'm just going to go ahead and I just want to point out.
continuing on into the Susquehanna River, where other people's houses. So
Yeah, there's houses on the other side here. So you can imagine it's an open field like a park, and these guys are just shooting Civil War weapons off. But notice the cannonball actually gets lodged into a tree, and it might be hard to see in the video.
go in so much as they go up and keep going. So if you look up here, there's the ball is lodged in the tree. Oh, gee.
It does show just how much momentum that cannonball has. So, all right, a couple things back to the cars, because I always like to go to the cars because we drive cars every day. The Insurance Institute for Highway Safety tests cars, and this is basically engineers who are using momentum and energy in action every day. So just think about for a second what makes a car safe, and then who determines what safe is for a car, and then how do they check for car safety. So take a second to answer those questions, and then we'll watch some crash videos here. What things make a car safe? Basically, if you do a little research here, there's 4 fundamental things. Number one, since the 1960s, passengers are required by law to wear a seatbelt, because Newton's first law, you're an object in motion, you want to stay in motion. So the biggest thing, you got to wear that seatbelt to stay in your car so all the safety features can work. Second thing, back in the 80s, when I was a kid, they started putting airbags as required by law to be in a car, right? So the passenger is stopped by the seatbelt, and then they have a collision with an airbag that inflates in less than 1/10 of a second. And then there's exterior features. One, you're in a safety cage, which is basically like steel that's welded together, and you're surrounded in a cage. And as we talked about last time, outside the safety cage is what are called crumple zones. So there are regions that are purposely made to crumple, and that crumpling extends out the time of impact if you have a crash. And then the time of impact being high means your forces on the people in the car will be low. So those are the 4. You got seatbelt, you have the airbags, you have the safety cage, and you have the crumple zones. And if you're missing one of those, then your car is not as safe as it could be. Who determines if a car is safe? There's 2 primary groups. The government have a group called NHTSA, or NHTSA. Basically, it's a government agency that crashes most cars at different speeds. That's the government agency. And then you have a private group called the Insurance Institute for Highway Safety, or IIHS.org, and that's insurance companies that basically got together and said, hey, we want to verify which cars are the safest. And those are the 2. If you ever see a star rating, like this is a 5-star crash test, that's the government. If you ever see a group that's saying this is a good crash test, that's the Insurance Institute. So when you ever buy a car, someday make sure you look it up on both to make sure both sources say you have a safe car. I just wanted to show you the difference that some years can make. So 2004 Toyota Sienna is a pretty common car that I actually see in like our high school parking lot. Toyota minivan, which maybe makes sense because maybe that was like gifted down, like, hey, you can drive the minivan now. But take a look. This is the Toyota minivan, and this is from the Insurance Institute for Highway Safety, 2004. And at first it might be hard to tell, is that safe, is it not safe? But look at it, it's going 35 miles per hour, maybe 40. And you can see that crumple zone crumples up front like it's supposed to. The safety cage around the passenger, it doesn't, there's no intrusion. It's not the safety cage collapses, so it looks like you're pretty safe. And this car actually gets, I believe, a good rating. So it's the highest rating you could get at the time is good crash test. And the worst rating would be a poor. And the in between there's acceptable and marginal. But the Insurance Institute for Highway Safety says the best you get is good. Another vehicle that I've seen out in our parking lot actually quite a bit, not so much anymore, but it's a 1997 Pontiac Transport. So basically they're kind of two competing minivans. This one Toyota still makes. This one is not made anymore, and you'll kind of see why that is. This is the same speed, 35 miles per hour. And notice again, they had crumple zones, they have a safety cage, but the safety cage collapses. So notice the passenger is not kept safe because all that energy from the force gets spread into the occupant compartment here. And that's the same speed as a Toyota. So if you're going to buy these two cars and you're going to drive them around, you just watch this video and you'd be like, it's pretty obvious which one's safer, right? So I'd say that the safety cage failed in that case. Same speed. That's a Pontiac Transport. Again, that one's no longer made. Let's look at a different group of cars here. Let's go F-150s. I see a lot of F-150s. Last year, the number one selling vehicle in the United States, Ford F-150 pickup truck. So let's look at the older one first, 1997 to 2003. And again, you'll see lots of these on the road because it's been the number one selling vehicle for years now. You think a pickup truck would be pretty safe. That's the horn going off there. So this is an older F-150. And you can see that doesn't look so good. That white smoke is basically there's a chemical reaction that takes place inside the airbag that inflates the airbag really quickly. And just notice, I'm just going to back this up. That tire, notice how far the tire moves back. It moves back right to where your feet would be. See, it moves back about a foot, 2 feet into where your feet would be. So that's not good. So that they'd call that's intrusion into the occupant compartment. You don't want things going into where the person is. And you can see again the safety cage collapses, and this is only at 35 miles per hour. All right, so Ford was aware of this crash test, right? Because the Insurance Institute does it and they publish the results. So now, good news, 2015 F-150. Take a look at this one. They made some improvements.
The F-150 has been the biggest selling pickup truck for decades. Ford raised a lot of eyebrows when they announced that the 2015 model would have an all-aluminum body. The Institute has put the new pickup truck through its paces, from low-speed crash tests to higher-speed tests of front, side, rear, and rollover crash. Just
appreciate every time they do this, you're basically ruining a vehicle, right? And some of these trucks can be $50,000. So when you see them crash, the car companies actually donate their cars to the Institute to be tested, because if they get tested and they get certified that they're safer, then you can sell them or market them as a safe vehicle. So every time you see them crash,
to higher speed tests,
$50,000 vehicle there.
The Crew Cab, the largest selling variant of the F-150, aced all 5 Institute crash tests, including our new front small overlap crash.
So you can see that crash test, and that's actually at a higher speed. I think this one's now at 40 miles per hour because our newer tests to go at a little higher speed. You can see there's a lot of damage up front. That crumple zone did its job. It crumpled. It absorbed all that force over a big time. That impulse kind of dissipated. But there's no crumpling in the safety cage. Now you have airbags all the way back. So definitely safety improvements here. And I should probably say I'm not endorsing buying any car over another. I just say check out the Insurance Institute for Highway Safety before you buy a car, just to see how your car ranks. Because if you're going to spend a lot of money on a car, hopefully you're buying a safe one that you enjoy. All right, we'll stop there. We've talked about a lot of different topics, but momentum conservation, impulse, and then we kind of applied it to different situations around cars and trains and cannonballs. So hopefully you have a good idea of what momentum is. And then if you have any questions, as always, reach out. But we'll stop there for today. Have a wonderful day and go Physics All-Stars.